Hi there. Today we're going to be looking at techniques for evaluating limits. And this is a very exciting section for me because we get to use so many little pieces of things that we've studied throughout our algebraic time together that kind of all come to, we get to practice them in this section. So in the last section, we saw that direct substitution and when we were performing operations with limits can be used for what I'm going to say are well-behaved functions. When I'm talking about a well-behaved function, I'm talking about something that's smooth and continuous. So it doesn't have those discontinuities, okay? So smooth and continuous at a specific point. So if we're looking at the limit as x goes to c, it's going to be smooth and continuous at least at that point, okay, at that value. And we know that if we have polynomial functions, that if p is a polynomial function and c is a real number, that the limit of the polynomial as x goes to c is just the value of the polynomial function at c. And as long as our denominator is not 0 in a rational function, then we can do the same type of a thing in a rational function. So we're just able, again, to use direct substitution. So let's just review that real quick. This is asking me to find the limit of x squared minus x plus 2 as x approaches -3. So if we try to apply direct substitution, I'd have -3 squared minus -3 plus 2, so 9 plus 3 plus 2, that gives me 14. So we didn't have any issues finding the limit by direct substitution. Let's do the same thing here. Sometimes with rational functions there's an issue, but notice that if I substitute 1 in, it does not make the denominator 0, so we can probably go ahead with the direct substitution. So I'm going to have 1 minus 2 times 1 minus 3 times 1 squared over 1 plus 1. So that gives me 1 minus 2 minus 3 over 2. So -1 minus 3 is -4 over 2, which is -2. Okay, so this wasn't a problem. Okay, however, if we look, let's suppose in this second example that we were asked to find the limit as x approaches -1. That's going to be an issue, right? Because -1 is a 0 of the denominator. If we use a table, however, just like we did the other day, what we would find is that the limit of the function as x approaches -1 is 4. And remember, what we could do is we could find values that are very close to -1, like above and below, like 1/1000th away, 1/100th away, 1/10th away, and make sure that it's approaching that same value. If we do that, it's going to be approaching 4. Okay, but that can be a little tedious and time consuming, and we don't always have graphing calculators at our disposal. So another way that we can find this limit of the function is to factor the numerator and to divide out the common factors, okay? And so that's this dividing out technique, is for us to factor the numerator and for us to divide out the common factors, all right? So if we were to take that, I'm going to take the limit. I'm going to rewrite this in the standard form for the numerator. So -3x squared minus 2x plus 1 all over x plus 1. For me, writing it in that standard form just makes it a little easier to factor. Okay. When I'm doing all of these simplifications, next I'm going to factor out a -1. I want you to notice that I'm keeping the limit notation throughout. Okay, that's an important thing. So now let's try to factor 3x and x, 1 and 1, plus 1 minus 1, and then x plus 1, okay? So when I look at this in factored form, what I see is that the numerator and denominator have a common factor. So I can factor out this x plus 1. And really what this will be equivalent to is the limit of the opposite of 3x minus 1 as x approaches -1, okay? And so now at this point, if I apply the direct substitution, I don't have an issue. So what I can do then is then substitute this 3 times -1 minus 1. Or you could have distributed and used -3x plus 1. I don't care. In that case, so we get -3 minus 1 is -4. And so that gives us that limit of 4 without having to use the graphing calculator. Okay. Notice that these two functions agree at all values of x, except for when the denominator is 0, except for that value of x equals -1. So that means that we can use this simplified function to help us out. So this is our f of x. I'm talking about that here. This is our f of x. And then once we have it all simplified down, this is what they're referring to in this statement as the g of x. Okay. So what that means is that by using the dividing out technique, by dividing out the common factor, we kind of create a new looking function. That new looking function is g of x. And what we can do is we can use g of x to find the limit of f of x at that point that's undefined. Okay. One thing to keep in mind is that the dividing out technique should only be used when direct substitution produces 0 in both the numerator and denominator. So this resulting fraction, which is 0 over 0, has absolutely no meaning as a real number. And this is called the indeterminate form. Okay. When you encounter this indeterminate form by direct substitution into a rational function, what you can do is conclude that the numerator and denominator are then going to share a factor. Okay. So in this case, we're going to use the graph to determine the limit visually if it exists. Then we'll identify another function that agrees with the given function at all but one point. Okay. So if we were to graph g of x equals x cubed minus x over x minus 1, let me do that real quick. Okay. We can put x cubed minus x divided by x minus 1. I'm just going to zoom 6 this for right now. And it looks like it's totally fine, right? However, if we look at our denominator, we can see that there's not going to be a value at x equals 1. So if I'm going to draw this, just to kind of like a little sketch here, it looks like there's like a little hole here-ish. Okay, I'm not sure where that is. But we can see that it's going to cross at 0, kind of go up like this, etc. So it looks something like that. Okay. So as far as the limit, if it exists, we can see that it's going towards here. We can look at that in the graphing calculator. But let's, so it looks like this is at about 1-ish, maybe 2. Hard to see. If we trace the function, for example, we can go here. We can see, oh, as it gets closer and closer to 1, maybe it's 2. So graphically, we can say that. But what let's do, just like we did in the dividing out technique above, let's identify another function that agrees with the given function at all but one point. And so what we can do to do that is factor. So if I factor this numerator, I can factor out an x. I end up with x times x squared minus 1 over x minus 1. So if I factor this, I have x times x plus 1 times x minus 1 over x minus 1. And what I can see is that these cancel. And so if this was my g of x, this time g of x was the original, so we can call the new one h of x maybe. That h of x would be x times x plus 1. Okay. And so what we can do is we can use this function basically to find the limit at any of these points if we wanted to. Okay. What we can see here is that the limit of g of x as x approaches -1, if we looked at our graph here, this is where our -1 was. I should have marked that, sorry. We can see that graphically that gives us 0. And we can see that if we used h of x, if we used direct substitution, if we found the limit as x approaches -1 of x times x plus 1, that gives me -1 times -1 plus 1, which also gives 0. So notice that both functions give us the same limit. If we look at the limit of g of x as x goes to 0, we can see here that that is going to be 0. And if we use our h of x, if we take the limit of x times x plus 1 as x approaches 0, that gives me 0 times 1, which is 0, so that matches as well. And here on the graph, it's just kind of hard for us to see. Again, we could have traced like we did on the graph. It looked like it was close to 2. So instead of doing that, what we could do is we could take the limit of x times x plus 1 as x approaches 1, and then substitute that in. That would give me 1. 1 plus 1 is 2. That would give me 2. So what that tells me is that graphically, there's going to be a hole there at that 1, 2. Okay? So there are lots of other techniques that we can use to help us find the limit of these functions, right? So some other techniques for finding the limit of functions where direct substitution yields something over 0 include rationalizing the numerator. What? I know in the past what we've done is rationalize the denominator, but the reason that we love that trick is because here in our limits, we're going to rationalize the numerator to help us out. Introducing the conjugate, and then also simplifying complex fractions. Okay, so this wants us, one thing that I'm going to say one more time is that we want to make sure that we keep the limit notation throughout. I know we're going to be doing a lot of substituting, and when we're doing all that substituting, that is going to be kind of annoying for us to keep writing lim over and over and over again, but the limit notation is required until we use the direct substitution. Okay. Otherwise, one line isn't going to be equivalent to the other, so just be cautious about that, okay? So let's do some of these. All right, so we're going to find the limit if it exists. Our issue here is that we have the limit of the square root of x plus 7 minus 2 all over x plus 3. And we want that limit as x approaches -3. We can see that if we substitute -3 in, that's going to be an issue. We end up with a 0 in the denominator. So when we see a radical in the numerator, what we're going to do is employ the technique of we're going to rationalize the numerator. Now we rationalize numerators just like we would rationalize the denominator. So again, we'll use our conjugate. The conjugate that we'd have here is the square root of x plus 7 plus 2. And we'll multiply by the same thing in our denominator, the square root of x plus 7 plus 2. Okay, so now let's see what's left. If we look at what's left, again, I'm going to keep that limit notation, and let's multiply these values in our numerator. When we have a plus b times a minus b, well, I guess a minus b times a plus b, we know that that's the same as a squared minus b squared. So if I take this root x plus 7 squared, that just gives me x plus 7, and then 2 squared gives me 4. So I end up with x plus 7 minus 4 in the numerator. Now the denominator isn't quite as cute. We're going to end up with x plus 3 as this factor, and then we have that guy that we introduced, the square root of x plus 7 plus 2 that we introduced. Now, I don't need to see every single step, but I want you guys to notice something about the numerator. Do you see what our numerator really is? This x plus 7 minus 4 is really, if I were to simplify this, this is really x plus 3. And do we see now that we have a factor of x plus 3 in both the numerator and denominator? And so by rationalizing the numerator, what happened is that we created a factor that we could cancel out of the denominator. And let's see what's left. In our numerator, we have 1. And in my denominator, I have the square root of x plus 7 plus 2. Now, that doesn't look very cute. However, if I substitute -3 in, I don't get 0 in the denominator anymore. It's like magic. So at this point, now that we have this simplified, and we've gotten rid of the idea of 0 in the denominator, we can go to the direct substitution. So we're going to take 1 over, and then I'm going to put in here the -3 plus 7, the square root of -3 plus 7 plus 2. And then we can go from there. So -3 plus 7 is 4. The square root of 4 is 2. 2 plus 2 is 4. So that means that my limit is going to be 1/4. Okay. So notice that as I did all of the algebraic simplifications, I have to keep that limit idea in. But then once I use direct substitution, I can drop it. Okay. Let's look at another one. Number 5. Our issue is that if we substitute 10 in by direct substitution, once again, we're dividing by 0. So what potentially could we do here? Well, one thing that we've gotten rid of before, regardless if we've had a limit or not, is we've eliminated complex fractions. So maybe we could do that. In this case, our tactic is going to be to simplify the complex fraction. And we know that we simplify complex fractions by multiplying numerator and denominator by our least common denominator. And what makes it the complex fractions is the x minus 6 and x minus 2 that are in the numerator. So I'll multiply by the x minus 6, x minus 2 in both the numerator and the denominator. Okay. So let's see what happens when we do that. So I'm going to keep my limit notation. And if I distribute this x minus 6 times x minus 2 here, the x minus 6 cancels, and I'm just left with x minus 2. And if I distribute it here, the x minus 2's cancel, and I'm left with -2, and then times x, times x minus 6. Then in the denominator, nothing cancels. I have x minus 10, x minus 6, and x minus 2. You guys, do not cancel these. The numerator isn't factored. You have to distribute and combine like terms before we do anything like that, okay? So we'll distribute up here. This gives me x minus 2. If I distribute here, this gives me -2x plus 12. And if I combine like terms here, that gives me -x. Let me write the limit. That gives me -x plus 10. And then I have the denominator is still x minus 10, x minus 6, x minus 2. Now, I hope you notice that there's something very similar in the numerator and denominator. Do you guys see that the -x plus 10 and x minus 10 are only they only differ by a factor of -1? I don't need you to rewrite this as like taking out the negative and then x minus 10 and then cancel it out. Hopefully we're savvy enough at this point to see that these are just have a factor of -1 that separates them so that we can just cancel it that way, okay? If you don't see that, let me know and I'll explain to you individually, okay? So that means that we're left with -1, and then we have x minus 6 and x minus 2 in the denominator, okay? So let's see if that works. If I put 10 in, am I getting 0 down here? No. So that means that it's time for direct substitution. So I can take -1 over. I can take 10 minus 6, which is 4, and then 10 minus 2, which is 8. So that gives me -1 over 32. Okay. Okay. Is this fun? All right, number 6. In number 6, the issue is that if I tried to substitute 7 in, I won't go through the motions with you, but if I tried to substitute 7 in, we would end up getting 0 in the denominator. Now, in the other cases, what we did is we tried to factor. The issue is that the numerator looks like it's pretty factorable, right? So we could try to factor. I'll do that over here. I can see that I can factor this by grouping in the numerator. So I could take an x squared out here, minus 3 here, and then I end up with x minus 7 and x squared minus 3, okay? However, if I try to factor in the denominator, I'm not so lucky, right? If I tried to factor by grouping, there's not going to be much that is going to be an issue, okay? So how in the heck are we supposed to factor the denominator? Well, I have a trick for you, my friends. What we're going to do is use synthetic division to help us factor, okay? So there are probably several factors that this has. So I'm going to put 3, the coefficients, negative 20, negative 11, and 28 here. And you might say, Mrs. Mackey, what am I supposed to do? I don't really want to do the P over Q stuff. You guys, you don't have to. I want you to look at what we factored. Do you see a 0 that pops out? If I look at this factored form, do you see that x minus 7 is a linear factor? And in synthetic division, we can divide by those linear factors, right? So because x minus 7 is our linear factor, let's see if we can use synthetic division with the x minus 7 to help us out. So I'm going to bring down the 3, multiply and add, multiply and add, multiply and add. Oh my goodness, so much fun, all right? And so what we see is that we have this factored form. Maybe up here I'll leave this as the 3x cubed minus 20x squared minus 11x plus 28. But then once we get to this step, we can use this and see, look, x minus 7 does divide into it. I'm going to use x minus 7 as one of the factors. And then the other factor is going to be 3x squared plus x minus 4. And now what happens is that these guys cancel. And so I have then the limit of x squared minus 3 over 3x squared plus x minus 4 as x approaches 7. Okay. Now, let's see what happens if I substitute 7 in this time. We don't get 0. So we'll do that. And again, you can use your, your scientific calculator or your brains to figure that out. But just for time's sake, we'll just go right to the direct substitution because I know it'll work out. So we're going to then substitute the 7 in. So I have 7 squared minus 3 over 3 times 7 squared plus 7 minus 4. So this gives me 49 minus 3. 49 times 3 is at 147. Yep, okay. 147 plus 7 minus 4. So this gives me 46. This gives me 154 minus 4 is 150. I can divide each of those by 2, and I get 23 over 75. Okay. So again, even though, so we used the dividing out technique, but this time we didn't know how to factor necessarily this bottom one on our own. So we factored the top one to kind of give us a little hint and to use synthetic division to help us out. Okay. In number 7, we have the limit of 1 minus cosine x over sine of x as x approaches 0. If we put 0 in, we should know that the sine of 0 is 0, so that's going to be a problem. So what the heck are we supposed to do? We don't have anything like irrational. We don't have any complex fractions. There's nothing to factor. What the heck? Well, in this case, another tactic that we can do is to introduce the conjugate. we know that conjugates can give us some super fun things sometimes, right? And especially when we're dealing with trig functions, though there are perfect squares that pop up that can be really helpful to us, right, with the Pythagorean identities. So what we're going to do is introduce the conjugate. And notice it's the numerator that would have a conjugate. If we had 1 minus cosine x, we're going to put 1 plus cosine x that's here. Okay. And let's see what that gives us. So that's going to give us the limit of, we can see this is going to be 1 minus cosine squared x over, and then we have sine of x, and then 1 plus cosine of x. You guys, in the denominators, by the way, you guys see I'm not distributing. That's like a waste of your life, okay? Our goal usually is to do something to the numerator, keep the denominator factored so that we can cancel things out, okay? All right, so I have 1 minus cosine squared x over sine of x times 1 plus cosine of x. Well, how does that help? Now, what some people do is they factor this and then cancel that out, and you're back to square one. So don't work backwards. But is there anything else special that you see? You guys, this is one of our very favorite Pythagorean identities, isn't it? How could we rewrite 1 minus cosine squared x? Hopefully, we remember that that's going to be the same as sine squared x. So we can rewrite that as sine squared x over sine of x times 1 plus cosine of x. And how does that help? Well, because the denominator is still factored, I can cancel this sine of x from one of these sine of x's. And so now I'm just left with sine of x in the numerator. So I have my limit, and in my numerator, I have sine of x. And in my denominator, I have 1 plus the cosine of x. If I substitute 0 in, I am not getting a value of 0 in the denominator, so I can go right to direct substitution. So I'm going to take the sine of 0 over 1 plus the cosine of 0. Not that exciting, I know. The sine of 0 is 0. We know the cosine of 0 is 1. It doesn't matter what's in the denominator. We're just going to get 0. But the point is that before we weren't able to take the limit by direct substitution, but we just move it around a little bit so that we can. All right. Okay, couple more. Like, this is my jam, guys. This is so fun because we're doing so much fun stuff. All right, number 8. The limit of x to the 8th minus 1 over x to the 5th minus x as x approaches 1. As you can see, if we put in 1, we get an indeterminate form. We get 0 in the denominator and in the numerator. And so what that means is that we're going to use, I hope you guys can see that right away, we can use the dividing out technique, which basically means we're just going to factor both. And these are factorable at this point. One special thing about x to the 8th minus 1, did you guys notice that that is the difference of squares? That we can factor that as x to the 4th plus 1 and x to the 4th minus 1. Now I get excited and want to factor x to the 4th minus 1, but I'm going to hold back. You'll see why. Then in the denominator, if I look, I can factor out an x, and I end up with x to the 4th minus 1 times x. Good thing I didn't waste my time factoring, because we see that we can cancel those factors out. So I just have the limit of x to the 4th plus 1 over x as x approaches 1. Now if I try direct substitution, I don't have the issue of 0 in the denominator. So I'm going to have 1 to the 4th plus 1 over 1. I can see that that gives me 2 over 1, which gives me a limit of 2. Okay. Oh, these are just so satisfying. Okay, number 9. We have negative exponents. You guys, what do negative exponents really imply? Those imply fractions, don't they? So if it helps you, go ahead and rewrite this as 1 over 3 plus h minus 1 over 3 all over h. Okay? So if we have the negative exponents, we can rewrite those as fractions, and then hopefully you see that what the issue is. Okay, if we try to use direct substitution, again, we have 0 in the denominator. So what we can do is deal with this complex fraction, right? And you don't have to write this each time. I'm just writing down what the tactics are that we're using. But that's what we're doing here. Once again, we're going to practice simplifying the complex fraction. So what we can do is multiply by the common denominator. So that's 3 and 3 plus h. I always use the monomial one first. And let's see what's left. If I distribute this to this first term, the 3 plus h cancels out, and I'm just left with 3. If I distribute it to the second term, the 3 cancels, and I'm left with negative 1 times 3 plus h. And then in my denominator, I have h times 3 plus h, so that's 3h times 3 plus h. Okay. Again, the numerator isn't factored, you guys. We could distribute and combine our like terms. This would give me 3 minus 3 minus h if I distributed. And I can see that 3 minus 3 is going to cancel. And so I'm left here with negative h. And then I have 3h and 3 plus h. Now that we've simplified, do we have any common factors? We do. I can cancel these h's out. And so I end up with the limit of negative 1 over 3 times 3 plus h. All right, so I've simplified as much as I can. Are we safe with direct substitution now? We are. So I can just use direct substitution, negative 1 over 3 times 3 plus 0, which is 3. So that gives me negative 1/9. Okay. One more of this super fun day. We're going to take the limit of x to the 4th plus 3x cubed minus x squared plus x plus 4 all over x plus 1. And we want that limit as x approaches negative 1, which we can see is going to be an issue, right? So what the heck are we supposed to do? It would be nice if we could divide them out. So the problem is that we divide out when we factor, and this is going to be difficult for us to factor because it's a quartic polynomial with 5 terms. So once again, what we can do if we want to divide out is say, let's maybe use this. We know that x plus 1 is a factor of the denominator that's causing an issue, right? Maybe that could be a factor of the numerator as well. So this is another case where we're going to use synthetic division to help factor. Okay. And so because we have this negative 1 that's here, well, the x equals negative 1 is the issue. We want to look to see if that factor of x plus 1 works in the synthetic. So a factor of x plus 1 means I'll put negative 1 here on the outside. I'll bring down my 1. I'll multiply and add, multiply and add. Didn't you guys miss this? It's so fun. Multiply and add, multiply and add. Dun, 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 dun. It works out. So that means that we could rewrite this as the x plus 1. And then now we're also left with x cubed plus 2x squared minus 3x plus 4, and then all over x plus 1. Okay. Yay. Because of that, we can just find the limit of x cubed plus 2x squared minus 3x plus 4 as x approaches negative 1. Again, this is that dividing out technique. The limits are going to be the same at one point. In this function, the limit at negative 1 doesn't exist. But at this function where all the other points are the same, we can like get an idea of where it's headed. So we can use that direct substitution, and we can take -1 cubed plus 2 times -1 squared minus 3 times -1 plus 4. So that gives me -1 plus 2 plus 3 plus 4. And adding all those together, I end up with 8. These kind of bled together. I apologize. Okay. All right. And that, my friends, is how we can use some of these algebraic techniques to find limits. I hope you guys enjoyed this section as much as I did. I know it looks so scary, but like it's so fun to like be able to practice all of these things that we've done, and like have a new like treasure that we can do. And our new skill is that we can find these limits. I do just want to point out one more time, I was very deliberate as usual in my color coding as far as like when I did the algebra, I kept the limit throughout the whole time. I'm only dropping the limit once direct substitution is legal. All right. So you shouldn't do stuff off to the side and then plop the limit back in. Keep that limit piece there the whole time. Okay. So yay, I hope you guys have good luck with this lesson, worksheet for homework, and have a great day. Let me know if you have questions. Bye.